In this video, we will discuss about chapter 5, which is image restorations. So far, I already mentioned in the earlier of this course that the image enhancement and image restoration, the objective of both process is similar. Okay, in other words, both is actually try to enhance the image, even they give a different name there, which is one is image enhancement, another one is image restoration. So there's a purpose why they differentiate between these two approach. Okay, as we discussed earlier, if we talk about the image enhancement, is a subjective process. Okay, why they call it a subjective process? Because as you can um, as we have discussed earlier, if you see the image enhancement, what we do is that once we get the input image or the image that is affected with certain noise and so on, so then we apply a very heuristic technique. What is the meaning by heuristic technique is that you do a try and error. Means that, let's say you apply for example, histogram equal, if you apply a power law transformation function, okay, for example, so you need to do uh, repeatably. Okay, that process means that once you apply the power law transformation function, if you see that the gamma is not suitable to be tackle that kind of problem inside that image, then you vary the gamma. Okay, that is what we call as a heuristic approach, means that you try and error. So you just put some gamma value there, and then if you find out the output is not good, then you try to vary again and again, and you will repeat that process again and again until you find the best output which is pleased by human eyes. Okay, again that is the evaluation process is kind of subjective there. Okay, however, for image restoration, it's in contrast with the image enhancement. Is when we talk about the image restoration, is an objective process based on estimating and modeling the degradation, and then apply the inverse. So what is meaning by this statement is here is that, okay, instead of you are just subjectively apply any suitable approach or filter to be enhance that image, what in image restoration, what we do later is actually we try to estimate or model the noise or factor that degraded your image before you apply the inverse process. Okay, the part which is inverse process over here is actually what we call as a restoration. So that's why the name for this process is restoration, is because of this inverse process. Okay, because when we apply the inverse process, is actually you want to restore back the original image. Okay, we try to restore back the original image which is not degraded by certain noise or certain factor that make your image is actually degradables. Okay, or any factor that have been degraded your image, we try to model that degradation model. Once you get the degradation model, then you apply the inverse process, where that is called the restoration, and that is the one that will inverse the process of degradation to get the original image, where that is actually free from any noise and free from any degradation factors. Okay, then later we'll discuss about this one. Okay, so that is the difference between the image restoration and image enhancement. Okay, the word restoration is because of you are restoring or you are doing inverse process to cancel the model which is make or produce the degradable or degraded image that you obtain, that is due to your imperfection in your imaging modality or in your camera and so on. So we try to model that, and we try to model the inverse process from there. Okay, now let's go to the discussion about image restoration in details. Okay, so the objective is to understand the characteristic of the signal and system so that degraded image can be recovered. Okay, this is what we have discussed earlier. again, this is the analog image which is from this environments. And what we do, okay, this is we imagine the process of, you know, obtain the image. Doesn't matter is it from your digital camera or from your medical imaging modality. Okay, this one is related to, still related, I think this one have discussed in chapter 1. Okay, imagine that this is our object, which is in analog image. Of course, when we talk about the analog image, is the image from the environment or from the surrounding, and then it will go into this digitizer. Okay, this is where you are doing a sampling as well as quantization. Okay, quantization, and then you obtain the digital image here. Okay, this is the digital image F there. So however, because of imperfection, okay, one of the factor that make your image is degraded is that because of the imperfection of your hardware. Again, this one is in this two block is actually is inside your digital camera or medical image modality. Okay, the one you should get is F, which is image which is free from the noise and free from any degradation factor. However, when you achieve the image or you obtain the image, you don't get the image F over here. Okay, if you try to model this one, but what you get is G. Okay, this is the one that you obtain at the at your camera, because remember this thing or these two block is inside your hardware or inside your digital camera. So once you snap, for example, once you snap, the one that you get is this one, this image G, where this image is not free from the degradation factor. So that's why we try to model back the process there. Okay, from the analog image here, you will get perfect image, perfect digital image, which is free from any degradation factor. But however, it's very difficult for you to obtain this one because of your hardware imperfection in your hardware. So that's why what you obtain at the final product of your hardware is this one, G, XY, which is the image that have been degraded with certain factor. Okay, so these figures show how we model or how we trace back the signal from the analog signal into digital signal, and now we obtain G. Okay, that just don't confuse with any the notation in here, because if you can see that in image enhancement, normally we use the F as the input image and G is our output image. But here actually if you talk about image enhancement, this is actually our input image. Okay, because this is the one that you receive from the hardware or receive from your digital camera. Once you snap, the first image that obtained by you and you save in your SD card is this one, G. Okay, so just don't confuse with that notation, because now we already use the F is over here, where the image, the digital image, which is after obtaining through the digitization, sampling, and quantization, then you obtain the image F. However, you don't get this F, which is free from degradation factor, because in general what you receive at the end of your hardware is this one, G, because G is the image the same image of F. However, it have been degraded. Okay, degraded with degradation factors there. So that's why we have some blocks there after degraded by your hardware, your imperfection in your hardware, so you only receive G over here. Okay, so now in image restoration, actually we want to find what is actually the process. This is what have been mentioned in this part, which is the inverse part. So the image restoration, now we want to the process the purpose of image restoration over here is that we want to do the inverse process, so we can inverse this process, the degraded factors there. So that's why the objective of image restoration, actually we want to get the f head here. So why we are using f head here? Because the objective of image restoration at the end, we want to make sure that we can obtain our f head which is very close to our f, because f now is the one that free from any degradation factor or degradation effects. Okay, in other words, we want to model this block so it can cancel or it can inverse this process, so we can achieve of course, ideally, if we talk about the image restoration, we want to get as this is the ideal one. Okay, if we can get this thing where your image f head here is equal to your image f, then that is the very excellent. However, in practical, you cannot achieve that. So in other words, the image restoration process, we want to make sure we find the suitable approach where actually that approach can obtain the f head here which is close to our f. Okay, so that's why we don't use f here, we are using f head, because it is just some estimation of our f. Because again, like I said, if your hardware don't don't have any imperfection or degradation effect, you should get a good quality image as f, because f is the one that you obtain after you performing the digitization, the quantization and sampling. But because of the imperfection, you don't achieve f, you don't obtain f, but you obtain g, where g is the one that affected with certain noise and affected with any degradation factor. So that is the purpose of image restoration. We want to have, or we want to produce some f head where the f head is close to our f, where the f is free from degradation factor. So what is the cause of image degradation? Okay, for that one, we talk about this one. What are the factor or what are the cause of our image degradation over here? Like I said, image degradation happen because of the imperfection of your hardware, and in general, this thing, image degradation can be list up. The cause of image degradation is actually can be list up into these four main cause, which is noise, where blur, illumination and optic aberrations. Okay, then noise is come from random fluctuation in the signal intensity, interfering signal from the electronic system of the capture device. Okay, again, because your hardware or your digital camera is in electronic system, of course there's a currents there. That's why when you capture the image consists of some noise that is due to the interfering signal from the electronic system. And another factor is because due to the blur. Okay, this one is the contribution of out of focus light to the imaging plan. So this one is related to lighting condition. Okay, because of when you capture some image, then because of the lighting condition that accept by your camera lens, then that will cause the image degradation called blur. And then you will also have some illumination, that is also because of the light. And then you also have the optic aberration, which is because of the things that inside your camera as well. However, in this course, we just focus on these two factors, which is due to the noise and due to the blur. Okay, we assume that our hardware is free from illumination and optic aberration. Okay, the one that degraded your image is come from these two factors, which is the blur and as well as the noise, or the noise as well as the blur effects. Okay, now from here, then we can try to model. Okay, again we try to model the process. So this is why in image restoration is more systematic as compared to image enhancement. Instead of you just give some idea on what happened, you also try to model the mathematical equation of anything happen anything happen to the image, started from the analog image until you receive at the end of your hardware, or at the end of your digital camera, for examples. Okay, we try to model what are the image degradation, or what are the cause of image degradation in mathematical model or mathematical equations. Okay, from here then, again like I said, in this course we only considered, or we only assume that our hardware is produce these two image degradation factor, which is one is noise, another one is blur. We assume that our hardware is free from illumination and optic aberrations. Okay, from here then we try to model the process there. Okay, the flows there. Okay, again this is our perfect image, which is free from any noise or any degradation factors. That's why that is notated by F. Again, don't confuse with the previous chapter. Now the notation is a little bit changed. Okay, F is not input image. If you talk about input image in image enhancement, actually in this block, it should be your G. Okay, because this is the one that you receive at the end of your hardware. You cannot achieve F, you cannot access F, because in general what you get is G, where this G is the degraded image or degradation image, where it have been degraded by two factors. One is blur, another one is noise. Okay, again we have two here, noise and blur or blurring effects. So if you model the mathematical models, okay, then this is how it look like. One is a blurring effect, which is represent this one, blur. Another one is the noise there, represent this noise. Okay, so that is how the degraded image G have been produced here. Okay, it's due to these two factors. That's why your image, the ideal image F here, you cannot obtain, because this image F have been degraded with two factors. One is blur and another one is noise. Then you only can access this one, because this one is the last part of your hardware. Okay, again this is inside your hardware. You cannot access it. Okay, this one is inside your hardware. So it can be your digital camera, or it can be your other image medical image modality like X-ray, CT scan and so on. So you cannot access this one. So what you achieve at the screen, or the one that you save in your SD card is this one. So this one you can access, however this one you cannot access. So that's why now the process of restoration itself, which is this part, we want to inverse this model, or we want to do some restoration, so then we can obtain the F head. Again, like I would like to highlight this one. This is the objective of restoration. We want to have our F head as close as Fx when we design our filter here. So this is the inverse part that we have mentioned in this first slide. Again, this first slide in this chapter. Okay, the inverse there is the restoration filter over here. Okay, so actually why we call it inverse, because we want to inverse this thing, both blurring and noise. So if we can inverse this thing, then we can obtain our F, which is close to our F there. Okay, our F head, which can be close as our F. So that is the objective, because we want to restore the image where we can make it the image. Okay, we produce some image where it is actually as close as our F, where our F is free from any noise and free from any degradation effect, or in this case it's free from noise as well as it's free from degradation function or blurring effect over here. Okay, that is what we call as a degradation or restoration model. Okay, so again, this is I would like to highlight here is that this F here is our ideal digital image, where that image is free from any noise or any degradation factor. And again, why we only have these two items, because like I mentioned previously, even the main cause of image degradation is consists of 4 items, and then in this course we only assume that the other factor or the other cause is we assume that our hardware is free from the other cause of image degradation. The one that degraded your image is it's caused by these two factor, which is noise as well as blurring effect, or we call it as a blur. It's come from which is in this things here, blur and noise. Okay, so that's why now this is the, this is what we call a degradation or restoration model. Okay, if you see there, actually this is degradation and this is restoration. Okay, you have some borders there. Okay, there's a borders there. Okay, there's a borders there. Okay, this is the restoration and this is degradation. Okay, from here I try to draw back this block in my whiteboard, whiteboard. Okay, this is the same things, the same block. This is degradation and this is restoration. And if you want to model the equation from this block, then you can see this is the equation that express the degradation model. As you can see, to get G, okay, G is the definition of G is actually G is equal to, okay, our H here, this is HMN here is a blurring effect or degradation function, where it will convolve with our image F, and this is what we get over here. Then you plus with the noise, so that's why you produce this kind of equation, meaning that if you talk about the image that you obtain G there, the one that you obtain from your hardware, can be modeled as, or can be defined as the HM convolve, the H convolve with F plus the noise. Okay, that is represented by eta over here. Okay, so that is how we express our degraded image G. And then from here, since this is the expression in spatial domain, again, if you want to convert it into frequency domain, then it will become something like this, where actually your degraded image G is equal to the multiplication of your blurring function or degradation function, which your F in frequency domain, okay, multiplication between H and F, then plus your noise, where that noise is in frequency domain, so now it become a capital N's there. Okay, that is how we express our degradation image G from this block.